Okay, let's talk a little bit about set theory. Set theory is in chapter 2 of the book, especially 2.1, and then also a little bit of it is in 1.3. It's actually part of Unit 2 in this course, and but I'm jumping ahead to Unit 2 because the rest of the stuff in Unit 1 I can't do easily from home. So I'm going to sort of skip part of it for now, move on to Unit 2, do that during this week while you're still not in class, and then when I come back, I'll go back and pick up Chapter 1, and we'll be already a little bit ahead of Chapter 2 by then. So do take a look at this. All the exercises that you would need to know how to do are on page 47 and 48 at the end of the first section of 2.1. There's a whole bunch of those that are in homework 2, and there's a whole bunch of those that are in test 2. You can actually look those up now if you want. Look up the homework sheet and look up the study guide for test 1 to find out what kinds of things I'm going to expect. Sets are pretty basic. You've probably seen them already. I'm assuming I expect you probably have, but I'm going to cover all of them anyway. Sets are the most important foundation of mathematics. When you go to try to decide what math is based on, sets is it. It's even more fundamental than numbers because you can't talk about how many of something there are unless you already have the concept of grouping it into a set to be counted. So sets are the most fundamental concept in all of mathematics. There is an area called Foundations of Math where they try to derive every single piece of math from the smallest number of axioms possible, and they start with 9 axioms of set theory called the Zermelo-Fraenkel theory. And or the Zermelo-Fraenkel axioms. And you can look that up if you want. But that's not discrete math, so we're not going to get into it here. What we are going to get into is sets in general. So normally we'll name our sets and list them this way. This would be a set containing 1, 2, 3, and 5. You could have, it doesn't have to be numbers. You could have letters, A, B, C is in this set. Or you could have concepts or colors or even other sets, anything you want in a set. You can have an empty set, which would be that way. We'll come back to that. You can have an infinite set. Okay. All those are sets. The main thing about a set is that order doesn't matter. So that ABC is the same set as ACB is the same set as CAB, and duplicates never count. So ABCB would still just be ABC. The duplicates would just not be listed as duplicates. It'd just still be 3 elements. So an element can end up in there twice. The method that I've been using up above is called the roster method, the method for describing a set. There's another way to describe a set, and that's using what's called the set builder method, which might be something like this. This would be a list of all the colors that there are. What happens here is instead of listing them all, we give a criterion that has to be met in order to be a member of the set. So anything that is a color ends up in this set. The way that's read is X is the set of all X such that X is a color. You can also do that with numbers. You can say set is the set of all X such that X is an integer greater than 5 or something like that. So we'll often use the set builder method, especially when we don't know what elements actually are in a set. We just know what the rule is for being there. In that case, often we use the set builder method. There are several famous infinite sets that math uses all across the board. I'm sure you've heard of them. Let me just mention them to you. The first one is n, the natural numbers, and it's this set. The second one is a w, which is the whole numbers. It's the same set but with a 0 in it. The third one is z, which is the integers. It's the same set but with negatives included. Generally speaking, I should have a comma before the semicolons after also. The fourth one is q, which is the rational numbers, which are fractions. Think of rational here as meaning ratio based. The typical way to define that is to use a set builder notation, something like this. You should say any ratio of an integer belongs in there. R is the real numbers. Sometimes people even go one step further and have C, sometimes it's not called C, as the complex numbers. Now, I'm sure you know that when you see these in books, they don't actually look exactly that way. They have a slightly different font. If I can find my pen, yes, here it is. I'll draw it for you over here a little bit so you can at least see what it looks like. Instead of just drawing N, like this, they draw n with a double line on the left, like that. That looks very sloppy, but you can imagine it. Or W, instead of just drawing W like this, it looks like this. I did that very sloppily. You get a double W. R looks like this, and so on. So you can imagine it much less sloppily than that. I'm sure you can see it in the book or any math book. Those are some very common sets that are used. All right, what else do I want to mention? How about I'm trying to just get my notes here to show up without having them show up for you guys, because I want to have a little bit more control than that. Okay. Sets of numbers, infinite sets, member of, and sizes. Let's talk about sizes first. Oh, I don't want to do font. Okay. We use the absolute value bars to mean size. So the absolute value of A, or the size of A, is 4. That is the size or cardinality of A, which is, i.e., the number of elements in it. So the cardinality of C, which is empty, is 0. Cardinality is a little more accurate word than size sometimes, because sometimes size isn't used to refer to infinite sets, and cardinality can. But I'll use size a lot of the time, and that'll be fine. I'll also talk about something like a 4 set to mean a set of size 4, and so on. An n set means a set of size n. So you'll see that occasionally when I talk. Let's see, what else have we got? Member. We'd like to say that 2 is an element of A, or member. 2 is a member of A, or 2 is an element of A. There's a special notation for that, which I'll use the tablet for on the right. If I can get it to work. Oh, come on. Here we go. My tablet's very not very sensitive here. So if I want to say 2 is a member of A, I'd say 2. And then is an element of symbol, looks like an E. 2 is an element of A. If I wanted to say 4 was not an element of A, I would say 4, is not an element of A. Okay. The empty set, by the way, has a special symbol of its own. It's the empty set, or the null set, and it's drawn either the way we drew it, as empty brackets, or as this symbol, which stands for the null set. Okay, let's see what else. 2 sets are equal if they have the same elements, exactly the same elements. A subset of a set is another set that is part of the first. Specifically, that should go in quotes because it's not well defined at all. We're going to define it. But the idea is pretty straightforward. If we have over here, come over here. Well, actually, I won't do it over here. I'll do it back on the other thing. A, remember, is 1, 2, 3, 5. If we had set D being just 1 and 5, then D is a subset of A. And that's written this way. 2 different ways, actually. Properly, it's written like this. D is a subset of A. But you could also say D, is a proper subset of A. So both those things are true. Come on. D is a proper subset of A. Means, i.e., D is a subset but not equal to A. So A is a subset of itself, but A is not a proper subset of itself. So over here, A is a subset of A, but A is not a proper subset of A. By the way, the null set is a subset of A and a proper subset of A. And the null set is itself a subset of the null set, but not, of course, a proper subset. Okay. So null set is a subset of everything. Everything's a subset of itself. Please notice the difference between subset of and element of. So 3 is an element of A, but the set containing 3 is a subset of A. 3 is not a subset of A because 3 is not a set. And the element containing 3 is not an element of A because A doesn't have a set in it. But if we add another set like this seems a little weird, but it's possible. Which had two sets in it. Now we could say over here that the set containing 3 is actually an element of E. Because E has sets in it, not just numbers in it. That seems a little strange, but in Zermelo-Fraenkel set theory, you actually have sets containing sets a lot. For now, I just wanted you to be clear on the difference. Let me say, one of the interesting questions is how many subsets does an n set have? The answer is 2 to the n. So it's worth, you can try to figure that out for yourself if you want. There's a lot of ways to prove that. I'll maybe prove it a little bit later on, as when we get to combinatorics, or we could do it before then. Wow, I really can't get this thing to work at all. But for example, if I have a set, oops, that's supposed to be set brackets, 1, 2, and 3, and you think of all the subsets there should be 2 to the third. Boy, I cannot get this thing to respond. 2 to the third subsets. Oops, ignore that. Pretend that says subset. So here they are. 1 and 2. 1 and 3. 2 and 3. Oops. Sorry again. Sorry, so sloppy. Just 1. Just 2. Just 3. And then the whole set is itself its own subset. Come on. And the empty set is always a subset. So there's 8 subsets. So that's true. It's always 2 to the n. If there's 4 things in the set, there's 8. There's 16 subsets. All right, what else do I want to do here? Let's talk about unions, intersections. If you have 2 sets, let's let A equal 1, 2, 3, 5 again. And just to keep things a little bit more consistent, let's let B be another set with numbers in it. So we'll have it be 2, 4, 6, 7. We can look at the union or intersection of the 2 sets. So union means put both together. Specifically, I'll show it to you in a minute, but here A union B equals 1, 2, 3, 5, but also 4, 6, and 7. It's 1, 2, 3, 5 because those are in A. It's 4, 6, and 7 because those are in B. 2 is in both of them. It, of course, doesn't show up twice because I said there's no duplicates. It just shows up once. So there's 4 in A, 4 in B. When I put them together, there's only 7 because there was one duplicate. The way that's written is like this. A union. It's like a big U. B. And there's something else called the intersection. That's written with an upside down U. A intersect B. A intersect B is everything that's in both sets. In this case, it's just 2. So the technical definition is A union B equals set of all x such that x is in A and x, or x is in B, and A intersect B equals set of all x such that x is in A and x is in B. Of course, I'm writing this on the left in words, so I'm avoiding all the mathematical notation. The way this would really be written, for example, the first one would be this, and this is what you'll find in the book. A union B equals set of all x such that x, is in A or x is in B, and vice versa. Again, apologies for my sloppy writing. You can find it in the book written much more carefully. Okay, let's see. It's worth asking yourself, what's the union with the empty set? What's the union of a set with itself? What's the intersection with the empty set? What's the intersection of a set with itself? If you think about it, A and B are always, well, if you think about it, A intersect B is always, well, let's do it this way. The size of A intersect B is always less than or equal to the size of A and the size of B, which are in turn less than or equal to the size of A union B. In other words, when you intersect things, they always get smaller or stay the same. When you union things, they always get bigger or stay the same. You might ask yourself, when does A intersect B stay the same size as A or B? And when does A union B stay the same size as A or B? Those are interesting questions as well. You should think about all that stuff. Okay, we need to talk about the universal set, the idea of a universal set, and a complement. A complement will be notated like this. A, oops, apparently I moved the whole thing with a bar over it. Okay, and that's A complement. Let's see. To describe the complement, we need to have the idea of a universal set. With any set, so let's use an example. Let's let V equals this set of letters, A, E, I, O, U. i.e. the set of vowels. Then we can ask, what is the set of non-vowels? And you might say the set of non-vowels is the set of consonants, which is B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, because I didn't include it in the vowels, and Z. But this would be wrong. Well, at least not well defined. Because what about 7? Is 7 a vowel? And the answer is of course not. It's not even a letter. So C should also have 7 in it. and everything else that's not a letter. So what is the set of non-vowels? It's huge. It's absolutely everything in the world that's not a vowel. Not just letters, but everything else. As a matter of fact, it's actually very hard to define. So it's not even clear that that's well defined. So what we'll do instead is we'll do this. We'll assume that every set is drawn from a list of possible set elements. V was drawn from the list of letters. That set of possible elements is called the universal set. What the universal set is depends on the context. So sometimes the universal set is letters. So if U, which is usually standing for the universal set, is the letters, and V is A, E, I, O, U, then the non-vowels are the consonants. And we have a name for that. All the non-V elements are called V complement. So over here, if we have a universal set of, say, let's call it U. If we had a universal set of, say, 1, 2, 3, 4, 5, and 6, and then we had a set A, which was, 1, 3, 4, then A complement would be, oh, good grief, would be 2, 5, 6. U complement, by the way, would be the empty set. And the empty set complement would be U. So let's see, what else do we know? No matter what A was, A complement complement would be just A again. So complements are worth looking at. There's a set difference operation where you say A minus B. The way that works is like this. We have something like, well, I don't even need the bar for the tablet for that because I can do that on the screen. If suppose the A gets again 1, 2, 3, 5, or let's do 1, 2, 4, 6 since I accidentally typed that, and B gets, let's suppose 2, 4, 5. Well, let's first of all do 2, 4, and then C, let's suppose, is 2, 6, 2, 5, 6. Okay, A minus B means you take A and then pull B out of it, so you'd only end up with 1 and 6. That seems clear enough. What's A minus C? Well, it's the same idea. You take A, 1, 2, 4, 6, and pull everything in C out of it, so 2 and 6 gets eliminated, leaving only 1 and 4. What I want you to notice is 5 does not get there was no 5 to be taken out, so it does not affect it at all. You don't put 5 back into A, you just leave it out altogether. Notice that, that this is not commutative. B minus A means you take everything in B and then pull out everything in it that was in A, which leaves you the empty set in this case. And C minus A in this sense, in this case, would be just the 5. So make sure, well, you don't necessarily have to do set differences a lot, but that's what they are. There's another operation called A cross B. It's called the Cartesian product. We'll use that a lot later on in the chapter. It's a little bit strange. The Cartesian product is the set of all ordered pairs with the first coordinate from A in A and the second in B. So if A is 1, 2, 3, and B is 5, 6, then A cross B would be a set of ordered pairs. The first ordered pair would be 1, 5. Second ordered pair would be 1, 6. And then 2, 5. And then 2, 6. And then 3, 5. And then 3, 6. I'm going to say a lot more about Cartesian products in a later video, so I'll not say much now. Okay. Let's talk about Venn diagrams. Venn diagrams are diagrams that can be used to to sketch the relationship between two sets. So a single set is represented by a circle. So let's suppose that I have a single set over here, A. I would just draw a circle, and everything in the circle, inside the circle would be A, and everything outside the circle would be everything not in A. That is, I would label the circle A, and then inside the circle would be everything in A, and outside the circle, if you think about it, would be everything in A complement. Okay. That's not what you usually do with these. The point is, when you have two sets, and I just cannot get my tablet to respond to me. Come on. When you have two sets, A and B, you draw the Venn diagram by drawing two intersecting circles. One circle for A, one circle for B. Leave them intersecting in the middle. So this is A, and this is B. And that divides the whole world into 4 groups. One group is the group inside both circles. If you think about it, that's A intersect B. And then there's the group, and then, cannot get this to work. Then everything in the A circle is in A, everything in the B circle is in B, everything in both circles together, which is that slot in the middle, is A intersect B. Outside of circle A is A complement, and outside of B is B complement. So if you think about it, outside both of them is A complement intersect B complement. A union B is everything in both circles, including all of both circles, this whole shaded area. That's a mess, but that's A union B. You can basically represent A, B, A minus B, A union B, A intersect B, B complement, A complement, B intersect, everything with A and B intersect, union, complement, or difference using Venn diagrams. And if you have 3 circles, 3 sets, you do the same thing. You just have 3 circles. You draw one over here, you draw the second one so it intersects it, leave a healthy amount of intersection, and then draw the third one so it intersects both of them. When you've done that, you've got lots of different pieces here. So I can say, for example, if this one's A, and this one's B, this one's C, I can say, for example, A intersect C. That would be everything that's in both A and C. That would be these 2 sections right there. Or if I said B union C complement, that would be everything that's in B but outside of C. So that would be this section right here and that section right there. And so again, you can draw, and if I wanted to say A intersect B intersect C, I can put parentheses around one of those, although it's not really necessary. That'd be everything that's in both A and B that's also in C. That would be this middle section right there. So again, you can use a Venn diagram to represent all sorts of different combinations. I expect you to be able to do that. Now, one of the things we'll do with Venn diagrams is prove whether things are equivalent to each other. So for example, one of the things you might be interested in, okay, I guess that's the last set of stuff I need to do here. For example, one of the things you might be interested in is finding out, actually I'll do a few more things here. Is A union B complement equal to A complement union B complement? That is, you could ask yourself, is A union B, the whole thing complement, equal to A complement union B complement? And one way to find that out is to do the Venn diagram for them both. A union B looks like this. That entire set, that's A union B. So A union B complement is everything outside of that. In other words, it's all this area out here. This is A union B complement. Over here, A complement is everything outside of A. So it's all this, but this part too inside B, it's all of that. And B, this is A complement. And B complement is everything outside of B. So it's all that including A. This is B complement. So both of them together is when you put both of them in the, you color them both in the same graph, be everything outside for sure, plus this part of B, because that's part of the first diagram, plus this part of A, plus that's part of the second diagram. This is A complement union B complement. And if you look, they're not the same. This one leaves out these portions right there and there, and this one puts them in. So the answer is, why will this not respond? I have no idea. Well, I can't write it up. There it is. Now I can. The answer is no. Okay. So, turns out, by the way, that there's a De Morgan's law for these, just like there is for logic. It is actually true that, oops, hold on, let me start down a little bit further. A union B complement equals, good grief, A complement intersect B complement. And that A intersect B complement, just really can't write on a tablet, equals A complement union B complement. And this is called De Morgan's law, just the same as it is in logic. All right, what else can we do? The book has a series of, I believe it does, let me go look. Theorem 2.1, and then later Theorem 2.2. You have several properties of sets. So those are, let's take a look at some of those. A says that union and intersection are commutative. B says that union and intersection are associative. C says that union distributes over intersection and intersection distributes over union. D says that the complement of the complement cancels. E says that a set unioned with its own complement gets you the universal set. F says that a set intersected with its own complement gets you the empty set. G says that sort of what we talked about before, that both A and B are at least are subsets of their union. And H says that both A and B, that the intersection of A and B is a subset of both A and B. And I gives an alternative definition of set difference. It says that to find the set difference A minus B, you can simply take the intersection of A and B complement. Each of those should make practical sense if you think about it. And 2.2, by the way, gives you De Morgan's theorems, De Morgan's laws. So how would you prove these things? Well, first of all, they should make sense if you think about it. Secondly, you could actually prove them by doing Venn diagrams. And I think I asked you to do that in some of the homework. You could just draw a Venn diagram for both sides and show that the two Venn diagrams are equal, and that would prove that they are, in fact, equal. The third thing you can sometimes do is to use the definitions of sets themselves to solve these. So, for example, doing it over here, which means I'm not going to be using the... So, for example, if I wanted to show A union B equals B union A, I can do this. I can say proof A union B equals the set of all X such that X is in A or X is in B. That's by definition of A union B. But that's equal to the set of all X such that X is in B or X is in A. Now, why is that true? Because OR is commutative. And we know that from our section on logic. And that is equal to B union A by definition of union again. So that one we can just prove by definitions. Some things you can prove by actually using the properties. So now that these properties are set in theorems for you, you're allowed to use all these properties whenever you want to. So for example, if you look at okay, no, I'll leave that alone for now. Well, look at example 2.4 on page 45, and you'll see the kind of thing I'm talking about. And the other thing that the other thing on this is, oh yeah, one of the things, if you do proofs, it'll be helpful for you to know that one way to define A equals B is to say that it means A is a subset of B and B is a subset of A. That's often either a definition for equality or it's given as a theorem. I think it's actually given as the definition for equality here. But let's see. I think that's all that I have to say about this. That's all there is to know about sets for now. Take a close look because we're going to build on this with a lot of other stuff. So I apologize for the sloppiness of my writing at times, but I think this will be enough that you can follow it.